Hello everyone, my name is Mark, and today I'd like to introduce you to a software that I've been writing called Dagster. Dagster is an open source software to solve SAT problems in parallel. Now I've designed this piece of software together with my colleagues at the Australian National University, and I'm pleased to present it to you today. So first and foremost, summary, Dagster is an open source SAT solving tool for SAT and model counting SAT problems. And the idea is that you give to the tool the CNF file that is associated with the SAT problem and a decomposition of the SAT problem into parts specified via a DAG format. The DAG specifies sub-problems for the CNF, which are then resolved together to solve the problem in parallel. Now, first and foremost, what is a SAT problem? So a SAT problem, or a satisfiability problem, is a classic computer science problem, which consists of a set of binary variables, so x1 to xn, and a set of constraints that those variables must satisfy. And a solution is binary values that satisfy those constraints. Now, satisfiability problems have been around for a while, and one of the most common ways that they are rendered is in a form called CNF. Right, so for instance, there on the screen, there is a CNF rendered format of two constraints. So the first constraint being that x1 must be true or x2 must be false. The second constraint is that x2 must be false or x3 must be true. This is CNF format, conjunctive normal form. And in computer science, the computers represent this in a Dimic CNF file, as represented down here, where the header pCNF of three variables and two clauses, respectively 1 or not 2 or 3, like you see here. Now, SAT problems are reminiscent of, can represent a lot, and there's many different kinds of problems that can be represented in SAT, depending on what those binary variables and their valuations actually mean. For instance, there's different tiling problems, so we'll bring up an example tiling problem. There's also like graph coloring problems, mathematical things like planning or pathfinding, and also, particular to us, we investigate bounded model checking of computer programs. But, basically any kind of problem that you can represent as being constraint satisfaction on binary variables, you can represent as a SAT file, a SAT problem. Now, one of the things about SAT formulation, particularly in CNF, or conjunctive normal form, is that it's not exactly clear what the problem corresponds to, and indeed many realistic problems have logically separated parts, or parts that more or less logically separate. Additionally, there might be different ways in which you could specify the problem to be solved, that is, execution ordering of the respective parts, and these are kind of typically absent from a CNF file. Dagster is designed to remedy this. Particularly, with Dagster, you input a DAG file that more or less explicitly separates the different kinds of subproblems that there are in a problem. So, for instance, on the left here we have an example of a CNF file, and then on the middle here we have a specification of a DAG structure represented by the graph on the right. So particularly the DAG, or the graph, directed acyclic graph, has 6 nodes, indexed 0, 1, 2, 3, 4, 5. And so node 0 is associated with the satisfaction of clauses, that is constraints, indexed 0, 4, and 6. Node 1, for instance, that is subproblem 1, is identified by the satisfaction of clauses 0, 1, 3, 4, and 6. 2, 1, and 3, 3, 1, 3, 5, 6, 7, etc. Now, additionally, not only are these subproblems solved via the software, but the solutions of one are passed as constraints to the satisfaction of another, specified by the direction of the arcs between the nodes. So, for instance, as specified here, node 0 connects to node 1, and the solutions of node 0 that are binding on the possible solutions of node 1 are the variable valuations to variables 1 and 2. Respectively, solutions of node 2 that constrain node 3 are variables 3 and 4, and etc. And then finally, the solution, or the terminal node of the DAG, is node 4, and any solutions to node 4, particularly reporting the variables 1 to 6, are actually reported as solutions to the whole problem. So this is a DAG, and it's input into Dagster. Now Dagster takes the CNF file and the DAG, and then schedules its workers that is the multiprocessing workers, to solve these problems in a parallel and online capacity. Right, that is, in an asynchronous manner, issuing work to solve particular nodes across a HPC architecture. So, as represented here. Now, what I'd like to do is I'd actually like to show you how Dagster is used in practice. So, let's go for a demonstration. All right, so let's do this. So I'm minimizing, and I'm going to a terminal window. So what I'm going to do, we're going to load up a Python wizard, which is a configuration. And then we input the respective things that we need to do. So /c1.text is an example of a C1 is a respective CNF and a DAG. So let's say, I'm running on my laptop here, which is not that spiffy, but let's say we have 4 workers, and then we want to output the solutions to my output.text. We want to enumerate all solutions. Then there's a whole bunch of options here, so we can do checkpointing or loading checkpoints for backing up. We have a choice of different CDCL algorithms for the workers, and the configuration of using them, and the configuration of the helpers then using them, etc., and etc., etc. And we want to save our configuration to my configuration.text, and then that will give us the respective command line to run, and then we run it. And bam, there we go. There's cat my output.text. Now, additionally, if we were to do that, we could do std io.h blah 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 std io.text. Right, and then we could load python viewer.py d1.text. Right. And we could see it actually displaying the workers going there. And look, the workers are complete. Cool. Alrighty, so back to the slides. Right, so the first thing is that using this software, which is very graphical user interface and has plenty of options, we can solve various problems. So in our paper that is submitted alongside this presentation, we have various case studies. So particularly, the first one is costas arrays. So what is a costas array? So a costas array is a mathematical problem where you have a grid and you have filled in boxes in the grid, like so. And the satisfaction of a costas array is that there must exist a thing for every row and every column, which you can see satisfied here in this example 6x6. And also secondarily, the displacement between any pairs of dots is unique. So for instance, this is 1 to the right, 2 down, and you can see that there are no other pairs of dots that satisfy that requirement. There are no other dots that are 1 across, 2 down. And you can do that for all possible pairs. Every possible displacement between every possible pair is unique. And that's the requirement of a costas array. Now, using Dagster, we can obviously solve a problem like this. It's obviously renderable in SAT. But furthermore, what we want to do is we want to also specify a decomposition of this problem into parts. So, let's play it simple. We say, okay, let part number 1 be the solving of the first 3 columns. That is, 1 box in every column, and the displacement between those boxes being unique. So the first stage of the problem is to solve that first 3 columns, and then the second half of the problem is to solve the remainder. Now, this is adaptable for any costas array more than 3, and what we can do is we can graph the performance of Dagster at model counting the different costas arrays of a particular size. So this is the example of the DAG for, let's say, a 5x5. So the first 3 columns of 5x5, variables 1 to 15. We have subproblem 0, respective clauses, subproblem 1, respective all clauses, and then we're interested in reporting all of the valuations of the costas dots themselves. So that is 1 to 25. Now, if we do that, we can basically, for different size costas arrays, from 10 to 15 here, which is getting pretty reasonable, we can see the different performances of Dagster with different modes. So Dagster has many modes of operation, and particularly here we report the performance across different sets of 3. So particularly, we could have done the decomposition of the first 3, or we could do the first 2. So that is the refinement of the decomposition that is possible, and we can see that we get different performances for Dagster. One of the things we notice, for instance, is that it outperforms the serial TinySat, which is good because you'd want 1500 cores of performance to do that. But it also outperforms an alternative model counting tool, specifically DMC model counting, as we can see on this graph. right? So costas model counting is an example use of Dagster. Furthermore, what I want to do is another application, so particularly a tiling problem. So pentominoes, they're like Tetris but with 5. So instead of 4 adjacent connected boxes, we have 5 adjacent connected boxes. And particularly a pentomino problem is to fill out a grid with pentominoes such that no pentomino crosses a bolded line, and no pentominoes of the same shape, that is counting reflections and rotations, touch each other. So you can't have an F pentomino touching an F pentomino filling in this grid. And so the idea is that we make a computer program to generate really, really big pentomino tiling problems, and we see how well Dagster performs. Now, one of the advantages of using Dagster is that, and particularly with tiling problems, is that Dagster can basically do this sort of thing where it solves regions iteratively and builds out the regions that it solves. So via actual regions of the tiling problem is a natural way of decomposing the solution process. And we have a choice of different ways that we can interleave the solutions of those region solvings together. So 2 different possible DAGs. Now, in this case, the pentomino tiling is uniquely soluble, and we can actually test that against different SAT solving problems. So this is a performance graph of Dagster running, against different competitive and parallel SAT solving tools. And as we can see, the blue line down below, that is Dagster with a mini-SAT running mode of decomposition B, as we can see, which is the one on the right, outperforms the rest by, a moderate degree, factor of 2, which is nice. So yes, you can do tiling problems with Dagster. Now, additionally, as a third case study, what we want to do is we want to demonstrate the use of Dagster to do basically bounded model checking on particularly protocol analysis. So one of the things is that you can basically, SAT problems can represent a whole bunch of things, but one of the things that you can do is that you can turn essentially C or programs and their control flow into a SAT problem. Now, one tool to do this is called CBMC, as GitHub link here. And the idea is that if you have a C program, you can annotate the source file with specific CBMC flags, and then CBMC will turn that into a satisfiability problem to see if the program can reach a specific error state set by those annotations. So for instance, up the top, we have a basic C program, and we have a C prover assert error state. Oh my error state. And so the question is there a path to that error state? And CBMC, if you pass CBMC test.c, it'll say, yes, there is a way to that error state, and then it'll give you the solution. And the way it does it is by converting the C program and its control flow into a SAT problem, and then consequently here it's solving with mini-SAT, which is a basic SAT solver, to prove that it's possible to reach that error state. Now, one of the things is basically the implication here is that you can do SAT-based reasoning on any logic which you can actually put in code, or at least in principle. And so basically, if you can render it in code, you can SAT solve it. And so one of the things that you can do is you can put in code, as we do, an emulation of a communication protocol between actors. So, if actor 1 sends a packet to actor 2, you can type that in code, right? Function actor 1 inputs to function actor 2 this particular header. And the idea is that, in the C program, you can set error flags for when the protocol is broken. And then consequently, if you've programmed it correctly, you can prove a path to an error and then consequently debug a protocol. Now, protocols can involve many elements, so packets and hashes and IDs and etc. And a hack may or may not depend upon specific elements, right? And so one of the things that we do is that we essentially code up a communication protocol, and we won't directly refer to it, but you can read the paper if you want to get into the details. We essentially code a communication protocol or an emulation of it with variables of 8, 16, 32, and 64-bit integers in the IDs and in the checks and in the hashes. And basically the idea is that the hack for a particular resolution may or may not correspond to the hack which is possible at a different resolution. And in this case we assume it is. So basically with, I refer to the paper, with this what you can do is you can prove that a hack exists at 8-bit resolution, and then consequently propagate those variable values, particularly the flags that control the ordering of communications, to a higher resolution, and then consequently prove that the hack exists at a higher resolution. So using this analysis, basically what we can do is we can show that propagating the hack from 8 to 64 bits saves almost an order of magnitude in terms of, decisions and assignments and conflicts encountered in the stat solving process, and is actually faster, right? So, but the implication being that for more complex communication protocols, by using this structured analysis, you can actually potentially debug protocols that you wouldn't otherwise be able to do via translating the solution between different resolutions and fidelities of variables. So this is another application of Dagster. You can do various protocol analysis with it. Now, this is broadly speaking, there's a lot of different SAT problems, and for a tool as general as Dagster, you can do a lot of playing around with it, a lot of toys. Anyway, it's an open source parallel SAT solver that solves based upon a DAG decomposition of the problem. And, as we show in our paper, it can solve discrete mathematics problems, tiling problems, and model checking problems, amongst a whole range of others. So thank you. My name is Mark, and Dagster, there's the GitHub link. Thank you.